Hey guys, welcome to another review club. And today we are reviewing PR number um,
28100.
28100. And this is about changing the crypto module into a new version of C++. So, yeah, let's get started. Stratus, for the stage is yours.
Okay. So the crypto module which we are dealing with is something called ChaCha20. First we'll briefly talk about what ChaCha20 is, and then we look into the C++ stuff.
Right. Okay, cool.
Yeah. So what is ChaCha20? Any idea?
It's an encryption algorithm
Yeah.
and like other kind of encryption algorithm, but I don't know what's the difference between ChaCha20 and say AED stuffs.
Yeah. AES. Okay. Yeah.
AES, yeah.
Yeah, so AES works pretty well, but like we always need a backup in case there's some security flaw with AES. So that's how the inventor of ChaCha20, his name is Daniel J. Bernstein. He's pretty famous,
In
like
cryptography world.
extremely famous.
Okay.
Like he's like a genius.
Okay.
Like he's the one who made this ChaCha20 like alligator stuff.
Okay.
Yes, so yeah, he's very famous.
So it's a variance of Salsa 20.
Yeah.
So that's like the mother variant of ChaCha20.
Yeah, he first wrote Salsa 20 and then he made some improvements and called it Chacha 20. And Chacha 20 is like very simple, very fast, and very secure too. And
Okay.
like the beauty is in its simplicity compared to like algorithms like AES.
Okay. Okay. Makes
Uh,
sense.
yeah, it's named after Latin dances. Like
Uh-huh.
Cha and Salsa, they're apparently Latin dances. So
Oh, nice. Yeah, I always wonder where does the name Chacha comes from. Yeah. Okay, cool. That's nice to know.
yeah.
So does Bitcoin have both AES and ChaCha?
When we use ChaCha, I don't know about AES. I don't think so. Let me check.
Okay.
Oh, it uses
Okay.
AES too.
Oh,
Yeah. So it has like a few other kind of modules like poly 1305
Yeah.
and those are like the same thing. I have heard somewhere like they use together like Chacha poly 1305 something like
Yeah.
that.
They
There
use
is a module
ChaCha
called
and
that.
Poly. Yeah, they call ChaCha. Like ChaCha is an encryption algorithm. Poly 1305 is like a authentication algorithm. So they use those
Okay.
together to get both authentication and encryption.
Okay, makes sense. hmm and then there is like just like this is probably side note. There is things like HMAC, HKDF, and MooHash. What are them?
No idea. I have not worked with any of them. So,
Okay, okay, cool, cool. Yeah. So let's go ahead.
uh, so just a simple thing. Encryption means it's like two-way encryption, right? You can convert data into something that's garbage and garbage back into data, right?
yeah,
That is
exactly.
encryption.
Yeah.
Okay.
Oh, your
And
question, the AES part, it seems like it's used in crypto, the wallet stuff which we looked at yesterday.
right, yes, yes. So like the master key encryption was happening via AES and stuffs.
Yeah, makes sense.
Yeah.
And ChaCha is used for BIP 324, is it?
Yeah.
Okay.
Right. Is there anywhere else Chacha is used for?
No, like
Only BIP
I,
324.
I'm only aware of the BIP 324 use case in
Okay.
Bitcoin Core.
Okay. Okay.
But this is widely used in the world as a good encryption algorithm.
Okay. And so this is like in Bitcoin code, the CPP file we have is like a re-implementation of the whole thing instead of using some libraries.
Yeah.
Okay. Makes sense. Cool.
Yes. Yes. So we'll first look into how it works, like just briefly, and then.
Okay.
Okay, wait. Which is my screen? Oh, this was the other meeting. Oh. Wait, why did I cut it? It had the diagram. Yeah, no way. Okay. Yeah, so ChaCha20 is like, so Emil was talking about like how we get ciphertext, the garbage thing.
Right.
So it's basically plain text. You can see it, right?
Yes, we can.
Yeah, so plain text, if you XOR it with some key stream,
Mm-hmm.
you will get the ciphertext.
Right.
So this plain text is the input and this is the output. So if we have a good way to generate the key stream, like
Mm-hmm.
we can get a good ciphertext.
Right. So the key stream is the one that is providing randomness here.
Yeah.
Okay.
And like if you want to get the ciphertext back, so like XOR goes both way. Like if you do plain text XOR key stream, you get ciphertext. If you do
Right.
ciphertext XOR key stream, you get back the plain text.
Right.
So we need the key stream. So ChaCha20 is an encryption algorithm which provides this key stream.
Okay.
So how do we get the key stream? So what ChaCha20 says is like it uses a block kind of layout. So there's like this 64 byte block which it makes. So this is like 16 boxes, right? 14
Right.
as 4 cross 4. And like one box here is like 4 bytes.
Right.
So there are like 16 boxes and each of them is 4 bytes. So it's totally 64 bytes.
Makes sense.
So what ChaCha20 does is like it tells you like as the input you have to give some key, a counter, and a nonce.
Okay.
So it fills the key here. So it uses 8 of these boxes.
Okay.
So one box is 4 bytes. So a 32 bytes key you need.
Okay.
Then this top part is filled using a constant. Like it's a constant. It's always a constant.
Okay.
The constant is expand 32 byte k. Like it's written in this paper. You can check it out.
Okay.
It's always the same. And then there's a counter. So like yeah, so this counter will keep incrementing. Like supposing you want to encrypt. Okay, I'll talk about like what counter is later. Like if it's the first box, like you'll use counter 0. If it's
Okay.
the next block, you'll
Okay.
use counter 1.
So as we are progressing through the key stream, we will like increase the counter one after another.
Yeah.
Okay.
Yeah, exactly. And then there's something called a nonce. So a nonce is the number used once. So it's like it's unique per message. So if I'm sending you one message, like it has to be something.
Okay.
So that's nonce, and that's also like 96 bits, 3 boxes.
Makes sense.
Is that a nonce? Like, can I like just check?
Yeah, definitely.
Nonce and counter.
So nonsense so that we can use the same key multiple types, right?
Yeah, exactly. Oh yeah, the nonce is a unique value per message.
Okay.
So like if I thought it was like to prevent replay attacks. Like if you send the same message many times, attacker could control some input. So you use the nonce to make sure that like there is some difference in the key string.
Okay.
I'm confused now. I think that's what a nonce is.
I think that is also correct, right? So that every time you encrypt, you should use a different nonce, basically.
Yeah.
So even though the message value might be same, if you're sending it twice, treat it as a different message. Yeah.
Yeah. Nonsense are bits of data, including this. Yeah, it should be used a single time with a particular cryptography key. In fact, reuse generally isn't prohibited, but the odds of reuse need to be exceptionally low.
Hmm.
Yeah.
So it is like randomly generated for each message and key.
It can be randomly generated or it can be like deterministically generated.
Okay.
In our
Okay.
bit324 use case, we actually deterministically generated, but in the music thing, it was like randomly generated.
Right.
Yeah.
Right. Hmm.
So it depends on the use case. Yeah, it's used to prevent replay attacks. Yeah, same thing we talked about.
Does nonce stand for number used only once?
Yeah.
Oh.
Yeah. That's what N1s is.
Okay, okay.
There is another thing called nums, which is called nothing up my sleeve number, but that's different.
Nothing up my sleeve. No. Oh.
Yeah, it's like it's used in Taproot. It's like you use a public key, a well-known public key whose private key is not known. Generally, they use the generator point as a nums. Like you cannot find the private key of the generator point. So, okay, that's separate discussion. Yeah, let's go
Yeah.
ahead.
So basically we were trying to get the key stream. So we were talking about that. So they make the key stream by having like this box of 64 bytes box,
Mm-hmm.
and they give the input, the key, the counter, and the nonce. And this magic happening in ChaCha20 is it scrambles. Like
Mm-hmm.
it's like there's a it uses AND, XOR, and rotate operations to scramble this whole thing.
Okay.
And
Okay.
yeah, so like that's the magic in ChaCha20. Yeah, this is what's happening. Like this is the scrambling magic. Like it looks very simple. Like they've taken 4 numbers, A, B, C, D. So 4 numbers would be something like this would be A,
Right.
this would be B, this would be C, and this would be D.
Okay.
So like what he's doing is like to A you're adding B, to D
Right.
you're XORing A, and to D you're
Rotating by 16 bits.
yeah. So the
Okay.
front 16 bits you take it and put in the back. And then it's again doing a lot of these operations. So it looks very straightforward, but like Daniel J. Bernstein has put a lot of thought into it. It's like it's designed in such a way that there is very less memory access. It's cache friendly. It's very performance efficient, and
Okay.
like he's done a lot of thought into it. And it actually has really good scrambling quality compared to the previous predecessor Salsa20.
Okay.
Like because stuff get updated twice.
Right.
So
So it has 4 additions, 4 XORs, and 4 rotations.
yeah. So this is actually a quarter round. So like 4 quarter rounds would make 1 round.
Okay.
Uh,
So
so
this whole operation happening 4 times.
yeah, so this is 1 quarter round. This violet thing we did, like we selected a column, right?
Right.
So this is 1 quarter round, and that is that operation which we saw right now. Like it does all this. So this is one kind of like this scrambling happens. So 1 round would mean like it does this scrambling for this, this, and this.
Right.
So that's like 1 round of scrambling happening. And yeah, so it's called ChaCha20 because it does 20 rounds of scrambling.
Okay.
So 20
So
is the number of rounds.
20 full rounds of scrambling like that.
Yeah. So so the first time the scrambling will happen like column wise. The next time the scrambling actually happens like diagonally. Like
Okay.
this will be A, This will be B, this will be C, this will be
Right.
D.
Okay. Okay.
So like 1, 2, 3, and then chooses one here. Here chooses one and 1, 3. So
Okay.
that's like again one round. So uh, then it will again do column, then it will do diagonal, column, diagonal.
Okay. It will alternate between column and diagonal.
Yeah, and like that 20 rounds will be done.
Okay.
In Salsa 20, actually, they used to do column and row, but then Daniel J. Bernstein like found out that doing it diagonally, it has some more performance efficiency or something.
Okay.
That's where we do diagonally.
Okay. Okay.
Yeah. So basically, it does this huge scrambling, and then it also adds this scrambled block back to the original block to make sure that it's irreversible.
Okay, so you had the original matrix. Then
Yeah.
after 20 round, you got the scrambled matrix, and then you add the scrambled matrix to the original matrix.
Yeah. And that's your final key string.
That's the final key string. Okay.
Yeah. So that's how you get the key string. And also remember, it's like 64 bytes. Like this one box is 64 bytes.
Right.
So you basically got only 64 bytes key string.
Right.
So supposing a message was longer,
Mm-hmm.
what would we do then? So then we'd have to like update the counter.
Okay.
So this was our counter. So initially it was set to 0.
Right.
So next we would make another 64 byte block.
All the other values remaining same.
All the other values remaining same, but counter would become 1.
Okay.
And but the thing is, even though it's just 1 bit difference,
But
because
it will
of this,
scramble the whole thing.
yeah,
Yeah.
that'll wreak full havoc and be
Okay.
totally different.
Okay. Makes
So
sense.
yeah, so if the message was 65 bytes, like we would have to generate 64 into 2 bytes of
Right.
key string, 128 bits. Out of
Yes.
that, 65 bytes would be used, and the remaining would like be just there.
Okay.
So that's how ChaCha20 works.
So like you also have to like store this final key string somewhere in order to decrypt the message, right?
Yeah, like yeah, so if I'm the encryptor, like if I'm the sender, I would know the key, the counter, and the nonce, and then I can make the key string.
Mm-hmm.
Like if you know the key, counter, and nonce,
Mm-hmm.
anyone can make this key string. So the receiver would also need to know the key, counter, and nonce to make the key string.
Oh, okay. So the receiver also needs to know the key value, and then he can perform the same operation and deterministically arrive at the same key string.
Exactly.
Okay, key counter and nonce, because
Yeah.
C is already constant for the protocol, so that doesn't change. Okay.
Yeah. And nonce also in BIP 324 we determine it deterministically.
From the message itself. Okay.
Yeah, like based on how many messages come, like there's some variable called packet counter. So like you can determine the both the sender and receiver would be able to like decide what the counter and nonce values. Like both of them would be able to arrive at the same value for counter and nonce.
Right. Right.
And key you get it using the Diffie-Hellman key exchange.
Makes sense.
Yeah, so that's ChaCha20.
Okay, that's ChaCha20. And so that operation is happening inside the ChaCha20.h, ChaCha20.cpp module.
Yeah.
Okay. Can we like make sense from the code where all this thing that you just explained, if we can see, or
Yeah.
it will be too difficult?
No, totally. Like I think that's actually a first question.
Okay.
Yeah, kind of. Like what is ChaCha20 encryption algorithm? Why are there two interfaces, ChaCha20 and ChaCha20Aligned?
Right.
Yeah, so yeah, so this is the header file. So ChaCha20Aligned. So they've used 4 bytes is 4 into 8, 32 bits.
Mm-hmm.
So this is like one box,
Right. So
right?
32 bits of an array of like 12 element array of 32 bits.
12 elements, yeah. So these are like our 12 boxes, uh,
Mm-hmm.
like this boxes,
Right. Okay.
because the first 4 boxes are a constant,
Constant. Oh, okay. I
so we are
see.
not using that.
Ah, makes sense.
Yeah, so this is input. So that's like a private member. And then public functions, you're saying our key length is 32 bytes. We saw the 8 boxes,
Mm-hmm.
right? Then the block size is like 64 bytes. The whole box, 16, the whole
Right.
16 boxes. Then, yeah, like this is another question. Like, should we do it now or later?
Yeah, so I think like this was part of the first question also, like why this is aligned. Oh no, this was the second one. Yeah, like we gotta get there later.
Yeah, we'll get that later.
Yeah.
This is a constructor.
Uh-huh.
You can initialize it with the key. Destructor, there are the functions to set the key
Uh
and
this is
32
the
byte.
nonce.
Yeah. So the nonce, we know it's like the last 3 boxes.
Mm-hmm.
Is it even possible to understand anything?
Yeah, we can't undo here in the white box, I guess. But yeah.
Yeah.
But that's okay.
Yeah, this is our nonce. I don't know what it.
Yeah, makes
Yeah.
sense. The last
It's,
3 bytes.
yeah, 3
The
boxes.
3 boxes. Yeah.
So that's each box is 4 bytes. So that's 12 bytes. And that's 96 bits.
Mm-hmm.
So that's why it's called nonce 96.
Right.
And it has this unique structure because that's the way it's used in BIP 324. But
Okay.
yeah, it's just a 96-bit number.
Okay, so it has like a pair of 32 and 64, but it
Yeah,
doesn't have to be like that, but it's used in that way for some other optimization later on.
yeah.
Okay.
This is seek function. It's like a way to set the nonce and the counter.
Mm-hmm.
And then a way to get the key stream. And
Right.
then the way to encrypt a message.
Right. That's pretty simple interface.
Yeah. So this is called ChaCha20 aligned. And like you'll notice here, like they've always written here, the size of the input and output must be a multiple of 64 bytes.
Okay.
Block length.
Hmm.
Even the key stream, like everything is a multiple of 64 byte boxes here.
Okay. And the reason for doing that is optimization?
Yes.
Okay.
So this is ChaCha20. This is like, this is the interface we interact with.
Right.
We interact with ChaCha20 and ChaCha20 interacts with this
ChaCha20
ChaCha20
aligned.
aligned.
Okay.
So ChaCha20 has this object of ChaCha20 aligned. And it also has 2 other stuff called mbuffer and mbuffleft. So this mbuffer is like, remember we talked about, like supposing that there's a 65 byte message.
Mm-hmm.
Yeah, if there's a 65 byte message, like if we use ChaCha20 aligned, we would have to generate 2 huge boxes, right?
Right. For 64-bit byte each.
Yeah, 64 byte each. And the counter here would be 0, the counter here would be 1.
Makes sense.
And they will do the scrambling and addition. And we would get 64 bytes key stream here and another 64 bytes key stream here.
Mm-hmm.
So that's totally 128 byte key stream. But our message is only 65 bytes. So we would use like all the 64 bytes from here, and we would use 1 byte from the next box.
Okay. Right. Makes sense. Because we
Makes
want
sense.
65 out of it.
Yeah. But we don't want to waste all this.
Right.
We should save it somewhere to be used later, like when the next message comes.
Ah, okay.
So that is saved inside M buffer.
Okay.
But for the next message, the nonsense stuff will be different, right?
For the next message, like okay, we need the nonce to make the key stream, not for the message.
Okay. Like this next message is it like the extension of the same message or like a completely new message?
Yeah, like if there's a completely new message coming in, like if you want to encrypt it again, like we can just use this key stream buffer, right?
Right. Okay.
So we would use bytes from this M buffer. Like if the next message is 3 bytes,
Mm-hmm.
if the next message is 3 bytes, we would then use 3 bytes from here.
Mm-hmm.
And so we have used 64, like you have 64 bytes, 1 byte, 3 bytes, and then this remaining would be in M buffer.
Right. Okay.
So I guess the receiver would have to get the first message and the second message as well. So if the receiver only got the first one, there is no way like they can calculate the second one, right?
Yeah.
Okay.
I think TCP, like at least in Bitcoin nodes, we do a TCP connection, right? So that kind of has this assumption that it's reliable and like the other party gets the communication.
Okay.
Okay, got it. Yeah, now it makes sense. Yeah, it's better to store it in buffer than waste it. Yeah.
Yeah. Look at it. Yeah.
And basically, like if there's a, I think it's an ACK and NAC, right? If there's a NAC, just throw everything and start over, I guess. Same
Yeah.
TCP/IP.
Yeah.
Mm-hmm. Makes sense. Okay. So that's where our buffer comes in.
Yeah. And then we also store the buffer left. Then there are public functions. Again, key, a constructor, a destructor, ways to set key, way to set nonce, block counter, way to encrypt messages, and way to get the key stream. And here, like, there's no problem. Like, you can encrypt any length message.
Right. Okay.
And whatever leftover key stream is there, it would be saved inside M buffer.
Okay. Okay. And how will we decrypt? That doesn't seem like an API.
Yeah, that's the same thing. Like, it's just XOR function.
Okay. So, right, you just give the same message for encrypting and decrypting, and you give the same key stream, and then you call the same function.
Yeah.
Also, encrypt does decrypt as well, basically.
Yeah, it's called crypt because it does both encrypt.
Oh, okay. Yeah,
Okay. Okay. Makes sense.
Yeah, so like we're not going. Yeah, so this is like the CPP file.
This is the same operation that they were doing in the paper. Okay.
Yeah, that same thing. They said repeat 10.
I think 10 for the row column and then 10 diagonal, is it?
Yeah, I think that's what they mean. I have to use this. Yeah, you're right. So 1, 2, 3, 4. Like this is our columns. So that's one round. And this is our diagonals. So 2 rounds.
Okay.
So 2 rounds, they're doing it 10 times. So 20 ChaCha20 rounds.
Makes sense. Okay.
Then they've like just written functions. Like this is setting the key initially the nonce and counter, everything is set to 0.
Mm-hmm.
This is where you set the counter and the nonce.
Right.
This is 96 bits and this is that.
Why it's called seek?
Why is it called seek? It's like, so initially this, they had two functions, like seek for seeking to a particular block,
Mm-hmm.
counter, and they had nonce, I think, for saying set nonce.
Mm-hmm.
So I think that happened in this. Okay, I don't know which commit he did it, but before there used to be like two separate functions, one for setting the block counter and another for setting the nonce.
Okay.
So when you set the block counter, it has this meaning like you're seeking to a particular block.
Okay. Okay. And then setting the value to it.
Yeah.
Okay.
So that's how that word came.
Mm-hmm. Makes sense.
Yeah, I think like in music playback and like video playback, we say if you want to fast forward, we say seeking. Right?
In general, also like in C++, also seek means like going to a particular location of a data structure.
Oh, okay. I did.
Interesting. Yeah. Yeah.
Okay.
Should we look at the functions, like how it works? It's kind of what you talked about.
Yeah, I think like it's kind of like what we talked about. Like then it's just doing it via array operations. And yeah. So taking them into some variables and setting those variables, then it runs a for loop. That those x0 to x3 I think are the constants.
Yeah, these are the constants. So remember, we need the original block so that we can add it finally, so that ChaCha20 operations are irreversible.
Right.
So that's where you store this initial stuff in J variables, J4, J5.
Right. Okay.
So this is the initial state we have already saved it up.
Right.
Then like X is the scrambling stuff which is happening.
Mm-hmm.
So this 0, 1, 2, 3, all this corresponds to our box numbers 0 to 15.
Mm-hmm.
And this is the constant and this is same as this. And then we play with this X to do the scrambling.
Mm-hmm.
So we do the 20 ChaCha20 quarter rounds. And then here is the final addition happening.
Right. Okay. It's
So
adding itself to the same constant values.
Yeah, like by this time X0 would have changed. So you have to put the original block over this scrambled blocks.
Right.
X0, this thing is the scrambled block, and this J stuff is the original block with the constants.
We could have wrote x0 plus equals to j0, right?
Yeah, but we didn't use it because anyway it's a constant and it's
right. Okay. Okay.
I think J0 is not there, no? Is J0 there?
No, they haven't.
That's not
Oh,
there.
okay. Yeah, they haven't even like initialized J0. Okay.
And then J12 is our counter. So we have to increment our counter after one, like 64 bytes is done now. It's this thing happening. Like it's 0, now it has to become 1. Like when it's the next block. And J is our original stuff. So that's why you have to change J12.
Right.
This is like kind of like there's a difference. Like supposing it overflows here, like this is actually 4 bytes, right? Supposing it overflows, like it's having this assumption that that these two boxes will contain counter values.
Okay. In case of overflow.
Yeah. So actually there are two implementations of ChaCha20. Like one of them says, like one paper says, like the original paper, I don't know which paper, like okay, there's one implementation where they say counter is only one box, 4 bytes.
Mm-hmm.
And these three things are nonces. And then there's another implementation which says these two are counter and the next two boxes are nonces. So like
Okay.
both are possible, like nonce 96 bits and nonce 64 bits only.
Mm-hmm. Makes sense.
And this implementation actually is, so initially we used to have only 64 bits nonce. Like before this PR, we had this ChaCha20 used to support only 64 bit nonces.
Mm-hmm.
So this PR kind of because it had 64 bit nonces, it had this line of code. That is, if J12 becomes 0, you have to increment J13.
Right. Okay.
Did you
Okay.
understand that?
Yes,
Like
makes sense. So
this,
if it overflows, then it becomes 0, and then in that case we set the next box to the counter, like increment the next blocks to +1.
yeah, and that was okay because it had a 64-bit counter support,
Okay.
like 2-box counter support. Now we use only 1-box counter support, but to make it compatible even with those variants, like it's still there.
Okay.
In
Okay.
the rare case it overflows, like it's not, at least in with 324 is uh, like we have guarantees that it's not going to overflow to these
It
two
depends on the
boxes.
message size, right? Like if the message length becomes too big, then you have to do that many counters.
Yeah, there's a limit on the message size. I think it's 2 power 24 minus 1.
Okay.
So that would fit inside this
Huh. Okay.
because this is 2 power 32.
Right.
8, 4 bytes?
4
4
bytes
into
of
8,
8. Yeah, 32
30.
bits.
Yeah,
Okay.
yeah. And then, wait, which function were we in? Yeah, it's just the key stream. So, like, you just copy this back into the key stream.
Okay.
And if blocks is 1. So initially, I think we started with how many blocks we wanted.
Right.
Like how
Output
many blocks?
size divided by block length. Block length is 64 bytes. So that means like multiple of 64s. How many blocks are there? Okay.
Yeah. So if we are at the last block, they want us to update the counter
Hmm.
because the next block will need the counter value. The counter keeps changing, right? We are not modifying any other value, but we are modifying the counters.
But this is like if only blocks equals to 1.
Yeah, because only at the last block we actually need to save the counter.
But what if
Because
blocks equals to 2?
yeah, we still have we are still playing with J12 and J13, and we are not losing that state. Like if blocks is 2, we will still be inside this loop.
Right. Okay.
So, and we have not lost the value of J12 and J13.
Okay.
Like when blocks is 1, we're going to return and we're going to quit the function and we're going to permanently lose J12 and J13. So they're storing it in input 8 and input 9.
Okay.
Because, yeah, we're quitting this function.
Hmm.
So this will decrement the block and increment the ciphertext and start filling the next 64 bytes place.
Makes sense. Okay. So that's how the key
Key
string
string,
generation is happening. Okay.
yeah. Encryption is the same algorithm. Like you have all these input states, you save it in J stuff, you have this loop,
Mm-hmm.
you know how many blocks you want,
Mm-hmm.
you save the constants, you save the J stuff into X, and you do the scrambling magic.
Mm-hmm.
All that happens here. And then before, like in keystream, we used to just
Right.
save it into cipher.
Now it's like doing the XOR operation.
Yeah. So it's basically the plain text XOR the keystream happening here.
Right. Okay. M is the message. So each
Yeah.
portion of the message is being XORed with X0, X1, X2.
Yeah, with the keystream. And then we need to store this XORed stuff back into the ciphertext.
Okay.
So there's just this additional thing being added into crypt, into
Okay.
encryption. Just the XORing of plain text and the key string. Rest
So
everything.
we can't use the earlier key string generation function here and then just XOR the returned value or something, no?
Yeah, we could, but then this is more efficient.
Oh, okay.
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 Like we don't have to store stuff or anything.
Okay, got it. Okay. Otherwise, you'll have to store it to this. Yeah. Okay, got it.
Okay. You were going to
Like,
do the operations anyway. So yeah.
yeah, in cryptography, people are like very conscious about memory access, cache friendliness, performance.
Yeah.
So try optimizing everything.
Okay.
And you know this ChaCha20 thing, like it is unrolled and kept now, right? Like they've written like like this many times.
Yeah. 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 You could have like, yeah, made another function to do the iteration.
Yeah, like this was actually a commit. Unroll the ChaCha20 inner loop for performance.
Okay. Okay.
And it's all written by one person whom we all expect to write this. Okay.
Yeah, before it used to be an I loop, and then he found out that if you do this macro thing, it has more performance. So,
Okay. Juice everything that can be juiced.
yeah,
Nice. Okay.
yeah. So, yeah, this. So we looked at crypt function too. Yeah, Mm, yeah. So we don't interact with ChaCha20 aligned. We interact with normal
ChaCha 20.
ChaCha20,
Okay.
and
We
it's
get
kind of
the key
simple.
stream inside this output array,
Yeah,
like output span.
yeah. Do you want to go into it? Like, it's not that
Mm,
hard.
yeah, it's not that hard. It seems
Wait, but
understandable. Yeah.
we're already at 2046.
Yeah.
Wow.
Yeah, time like flows fast when you are doing crypto. Yeah. Okay. Maybe like we can touch on to other questions.
Yeah, and
Yeah, so we answered the second one.
yeah,
Yeah, the third one was, can you pick out some examples of modern C++ code in the PR? And I think like that was quite obvious looking at the like the change set of the PR, like the many of the cases where it was like U32 unsigned chars, it turned into span of bytes.
yeah. So, like, what's span?
So, like, as far as I understood, span was like kind of like a pointer to a memory location consisting of like sequence of stuffs. Like
Yeah,
when we say like span of bytes is a memory location to, it's basically a pointer with a size of the slice
yeah.
that we want to talk about. So yeah, like so
This
it's
example,
yeah,
like,
so whatever was like a character pointer previously can be used as a span of byte.
yeah. Before we used to need to pass the size of the blocks to here, like we
Huh.
don't need to. We just span will already contain the pointer as well as the size of the block,
Right.
and it's
Right.
very good for contiguous set of objects.
What?
Like if you're storing anything contiguously, like an array or a
Okay, okay,
vector
okay,
and stuff
okay.
like that,
Right, right.
span is
So
very
like
good.
the requirement is like the memory location of those sequence of stuffs has to be like one after another. Like they cannot be haphazardly stored.
Yeah, they have to be one after another. And it has even more powerful operations to access like some parts of the memory location, maybe after 3 bytes. Like if you want to access the first 3 bytes, there's a
Hmm.
method called dot first. If you want to access memory after the first 3 bytes, there's something called
Right,
subspan. And all
right.
these functions are designed to be performance efficient. So that's
Okay,
why they recommend using it.
right. And this
We
is like
care
C++
about performance.
17?
I think so. I'd have to like check. Oh, it's C++20.
Oh, okay. So this requires C++20.
Interesting.
Isn't that a problem?
I don't know.
Yeah, because like I remember like there is like ongoing work of like making the whole library C++20 compatible,
Yeah.
but hmm, since
That's
C++20. But I have like seen like span being used somewhere else also, like 1 year ago somewhere in a review club.
Yeah, it's being used commonly. I expected it to be like maybe 17 or
Hmm.
not sure.
Okay. Okay.
Yeah. And then yeah, this byte, std byte, like that's also C++, modern C++
Yeah.
thing.
Yeah.
Like if you use
Previously they used to use character pointer.
yeah, and that's not a good representation of accessing raw memory because you can use addition and do all arithmetic operations on unsigned char. If
Hmm.
you're talking about bytes, it should only support bitwise operators like
Right.
and or
Right.
comparison operator. So
Right.
that's why byte is a much more nicer way of writing it
Hmm. Makes
and
sense.
safer. Yeah. And what else? Auto is like this
That's like
like
the type definition. It's like automatically inferring the type of a thing.
yeah. Like if you write, I mean, like if you write a wrong type, C++ compiler would anyway
Hmm.
complain and say, this is the actual type. It knows it, but it's not going to go and correct it for us. Like we have to
Right.
go and correct it.
Right.
Instead of that, just use auto.
Right. But like the problem with auto sometimes is like you don't get to see what is the type of key.
Mm, makes sense.
Yeah. It's the same problem with Python, right? You never know what X is until you run the program and make it crash. So but for some cases like probably it makes sense. So it's calling like parse hex of standard byte. So you kind of infer like it's a hex of bytes. So it's a byte string representing an hex.
Yeah. It looks like it's being used mostly in the tests,
Right.
not in the core stuff like
Hmm.
crypto module.
Hmm. Makes
It's
sense.
being used only in the tests.
Yeah.
No, except it's like uh,
It's like declaring like a function will not have any exception,
yeah,
and by that it means like it's basically a fail safe function, means like it will never fail or something.
yeah. And supposing an exception is thrown, the program will terminate instead of the exception being passed to another function and the program.
Right, so it will give a compile time error if you try to write an exception inside that function.
Yeah, I think so.
Make like, yeah, that's also I'm guessing, I don't know, but yeah.
I mean, it doesn't need to be compile time, right? Because like if you take crypt no exit, like the input and output would vary like at runtime too. Like the input would be different at runtime.
Mm-hmm.
And supposing at runtime it throws an exception.
Yeah, like there could be some memory accessing error or something also, right? Runtime stuff.
Yeah. So the program would terminate instead of uh, the exception being passed.
Okay, makes sense.
So basically, it's like if there's an exception, something very bad has happened,
Yeah.
and yes, there's
And
no graceful way to
it
deal with it.
shouldn't have happened, so stop the program.
Yeah.
Okay. Then it uses standard array. I guess like standard array wasn't there before.
No, array wasn't there before. Like Array is just like vector, except there's a fixed size for it. Vector with fixed size. So it was in C++11 apparently.
Mm-hmm.
So it's basically operates just like a vector, but
It
it's when
has
you
to be
know.
fixed size.
Yeah.
Yeah,
And
you
it has
cannot.
all this
Yeah.
cache friendliness, performance efficiency, all those stuff coming with it.
Mm-hmm. Okay.
Span is also same, no? What is the
Yeah.
difference in span?
But in span you have to be contiguous memory. Array doesn't require that. I'm
Is
guessing.
I don't
no, but
know.
how do you calculate? How do you calculate? So, from my understanding, is
I
array
think
is also
arrays,
continuous.
yeah, I think array is also contiguous. Yeah, array is also contiguous. So like you can actually pass both array or vector into a span.
Okay.
Like if you look at span, input output, the key, okay, wait, let's just look here. Okay, M buffer is an array. And it's passed to our ChaCha20 key stream, the aligned version of key stream.
Okay. And key stream. Okay.
And that uses a span.
Okay.
So we can pass arrays
As a
also into a
span.
span. Yeah.
Also, arrays might have more, I guess, functions on top of it, right? Is that
Arrays would have its own functions, vectors would have its own functions.
Right.
yeah?
And
So I'm saying more than span.
yeah, so that's
Span is
why
like the
like
primitive, I guess.
span
I
is
think
more
span,
efficient.
I think span has more functions than array.
Oh, okay.
Okay.
I don't know. Like it depends on the use case. Like span would have functions for any contiguous group of objects. Array would have only for a fixed, like only operations you'd need if you already know the size.
Okay.
So it again depends on your use case.
Oh, so for span, the size isn't constant.
There's no constant size. It can be as big or
Okay.
as. Yeah.
Oh, okay, okay. It's just that you can retrieve it, right? Okay.
Yeah. Like we use, like at least in Bitcoin Core, like we use this first and subspan a lot. So you can get the first n elements of the sequence, and
Right.
subspan is
In
like
between something.
yeah, after an offset, after the first four bytes. What's
Right.
the return? I guess, yeah.
Makes sense.
Uh,
Then that is no discard. I don't know what that is.
I also don't know. So they're saying it should be added when not using a return value is a huge mistake, and not using the return value is a source of trouble.
Oh, okay. So if like a function returns something, that return value has to be used.
Yeah.
Okay.
Oh, it's like the return type never in Java. I mean TypeScript. Basically, that function will never return.
No, it will always return and you have to use it always. I guess.
Yeah.
Oh,
Okay.
okay, okay. You're not okay. You're supposed to use it always. It shouldn't simply float around. Okay.
Yeah.
I think what you're talking about is option. Wait, what did you say?
What I said is like the function shouldn't return anything. Oh, that's void. Okay, so it is void return type, right? In C++, right?
Yeah. Yeah. I guess like no discard means like you cannot discard the return value. You have to like use it, store it, do whatever.
It's used mostly in the fuzzing stuff, consume random length bit vector.
Okay.
That goes against my freedom of coding.
What?
Oh, this guy.
Yeah.
Yeah.
Also in Rust, this is like by default the behavior. Like if a function returns something and you just call the function without like storing the return statement, then the compiler will say an error like you can't do that. And yeah, Rust compiler is very nagging. It nags about everything. So it nags about this kind of things by default. So you cannot like off it also. So yeah,
Have to.
you have to like put it in a dummy variable.
Mm.
Oh yes, the underscore, right?
Yeah, that's the
Yeah.
underscore. So let underscore equals to function call. So yeah. Okay, then it uses template, optional, constant expression. I guess like these were always there, right? Template, optional, constant expression.
Yeah, I think they, yeah, like I've seen it around.
Yeah. Yeah, I have seen around templates in the codes many places. Yeah, where it's like generic. You're defining generic types and generic functions.
Yeah, it can be any data type.
Hmm. Yeah.
So like here it's vector B.
Right.
It's default uint 8, but you could also pass anything else.
Right.
And when it compiles, it would make two versions, one with uint 8 and one with maybe std byte.
Hmm.
And that's less line of code, but easier for us, makes life easier for us too.
Hmm. Makes sense.
Optional is like if it's not necessary that a value
Right.
has to be written.
Yeah. It has some and none as a variant.
Yeah.
Hmm.
Context is like, is it? Oh yeah, key length, block length 64.
So it's something that is like executed at compile time. I always get confused about what constant expression is. It's something around like that's what they say, I guess.
We'll just search. Oh, it's there in since C++11. Yeah, it's possible to validate the value at compile time.
Right. So
I,
like it's only defined for expressions which can be evaluated at compile time. So it means like all the data that is required to compile it is already there.
yeah,
And I think it's also stored differently, right? At least in Rust, there's something will be stored with the program code itself and not in the memory. No.
In
yeah,
Rust, like there is no concept of constant expression.
Like in Rust, if you don't store it on heap and if
Oh,
you just put
like
constants,
so like you have to if you want to store it in the stack and not in the heap,
correct.
you have to like use something. Uh, wait, I forgot how to do that.
So I think it won't be stored in like the heap or the memory. It will be stored along with the program code itself.
Yes, yes,
Yeah.
yes, yes. Um, so yeah, so in Rust, like it will try to like store everything, like whatever it can, like at least the basic variables like numbers, arrays, vectors into the stack. And there is a specific function that you can called box. When you use that, it will then specifically store that number on the heap. So it will try to store as much as possible in the stack without like being inefficient, but then you can tell certain things to store in the heap. But that's, I think, very different from constant expression. But yeah, I guess like in C++, constant expression will be stored in the stack also. I'm just guessing.
Yeah, because it's calculated at compile time, right?
Yeah,
I mean,
it's
there should be
calculated
some.
at, yeah, it should be stored wherever in the program executable code is also being stored. So it's part of the binary basically. Oh, of course, in the RAM.
Yeah,
Basically anywhere. If the type matches a register type and the value is sufficient size that it can be loaded via a single load literal opcode, then the compiler could convert every use of the variable into simply loading the literal value into the register. So basically another thing it will do is like it will like not evaluate the expression anymore at runtime. It will just evaluate it once in compile time and store the result somewhere in the memory and use that result every time, like whenever we use that thing.
Mm, interesting.
Yep, lot of nuances going on. Yep. Anything else that is new apart from this list?
That's all I saw. Like,
Mostly like it was span and the standard byte,
yeah.
and other things are basically usuals. Auto constant expression template I have seen elsewhere also. Okay.
Yeah. Which version of C++ does Bitcoin Core support? What's the disadvantage of updating to a newer C++ version?
So I guess like it's 17 right
Yeah.
now, like the latest updated version. And
Yeah. It's supposed to be C++ 17. The 20 issue is still open.
yeah, yeah. But then again, like span,
Bad.
I have seen like span used elsewhere also, and I have definitely like compiled it with C++ 17 and it worked. So I don't know why span is C++ 20 in the doc.
I think new stuff was added. Is it for span in 20?
Maybe. I don't
So
know.
standard span replaces our span. So they have a like a span implementation somewhere else going on. So just up above, just above. Um, yeah, that issue point number second from the screen at the top of the screen.
Ah. Oh, right. Like, we have a file called span.h.
Ah, okay. So it's using our span basically. So it's a custom span implementation.
What? Like, we like actually have all this first. What? So we're actually using this. Oh my
Okay,
god.
so these are
Wow.
not standard function, but we are basically I remember somewhere like in a review club discussion, SIPA basically like rewrote it from the C++ 20 to like a custom implementation, keeping the API same so we can use it in C++ 17.
Yeah. Wow.
No
Yeah.
dependencies. Even C++. No
Yeah,
dependencies.
yeah, not even like on C++. So yeah.
It's really cool.
Yeah.
I couldn't believe it. Oh, it implements a subset of C++. Like, we never knew it.
Yeah, I now I remember reading like hearing about it in some review club. Like it was a reading club, like review club about span specifically, like when he introduced the whole span thing.
Wow. Okay. So, yeah, we are still in C++ 17.
Right.
Like, what's the disadvantage of updating to newer C++ versions?
Backward compatibility. Uh so
Yeah.
yeah, like if it won't run in like other compilers if it's everybody is not at C++ 20, right?
Yeah.
So if somebody is trying to compile it in older C++, then it won't work. Yeah.
It's mostly like a development decision. Like, it's only useful for people who actually build this thing from the code.
Right.
And it takes time for even the operating systems, the Linux distributions to update to the latest C++
Huh.
version. So
Right.
it's not good if we just update to C++20 and there's some OS which a developer uses which doesn't
Huh.
support C++20.
Right.
Some
Right.
compile. And there
Right.
were, yeah, I also saw this thing, like apparently there was some bug in C++17 and Ubuntu only backported the fix last week. Okay, this is 2020.
Okay.
So like bugs would like happen and there would be
Hmm.
backports happening and all those
Hmm.
issues.
Hmm.
So it takes time till that
It
uh,
stabilizes all over
stabilize.
the ecosystem. Hmm.
Yeah,
Makes sense. Who is this the uni guy? I have seen him in many old posts, but not
yeah,
recently. Oh, this is Corey Fields. Okay.
yeah.
Okay.
He's still there. He's very active in
Ah,
build
yeah.
system stuff.
Yeah. In build systems.
And then this,
So what does no except equals to delete? I couldn't figure out what does this mean. So there was like when it was changed, it was like no except equals to default, which got changed to no except equals to delete.
yeah.
And there is a comment that says like for safety, disallow initialization without key.
Yeah.
So what happens when it was default?
So when it is default, like you could instantiate a ChaCha20 without the key.
Okay.
But now when you say delete, like you're not even allowed to make a constructor without passing a 32-byte key.
Okay. Okay. So it's like explicitly disallowing it.
Yeah, it's like a safety feature.
Makes sense.
I think it was remove default constructors to make sure all call sites provide a key. I think initializing with an effective zero key should not be allowed by the interface of the class.
Okay.
Yeah, something like
Okay. That's like an extra safety feature.
that. Yeah.
Okay. Cool. So
That's
we covered ChaCha20 and all this question. It wasn't that hard. It wasn't that hard. Like thanks to your explanations on the whiteboard, it was like much clearer than what I was expecting.
it was simple.
Yeah. Yeah. Cool. So, yeah, we are at the end of our time. So, let's conclude it over here. Thanks everybody for joining in. And if you have any questions regarding ChaCha20 or like latest version of C++, drop a comment below our YouTube video and we will get there and try to answer everything that you can. Okay, thanks for everybody for joining in and see you next time on another review club.